Hello, everybody. So now we finally get to study a real mathematical concept, the first calculus concept, right? Which is called the limit of a function, right? And so this is section 2.2, and we'll go right into section 2.2. And again, I hope that from that introductory section 2.1, you have seen that this idea of a limit is quite important because it's used to define both the derivative and integrals. And so that is really the basic fundamental concept of calculus, right? Pretty much everything in calculus is defined in terms of limits. And so let's study what a limit is. And we will do an intuitive approach first in section 2.2, learn some theorems in section 2.3, and then later we will have a more precise, more mathematically precise definition of what a limit is. All right, but let's go right into section 2 and study the limit of a function. All right, so to introduce this concept of limits, let me just start with these three pictures. All right, so I have drawn the graphs of three functions. You may want to stop this and pause this for a little bit and then try to sketch these three functions, f1, f2, and f3. Now, for each of these functions, f of a is defined, okay? And so like, for instance, f of a here is 1. F of a here is actually not 1. This looks like 0.5. And here, f of a is also 1. See the black dot here? And the empty circle means that it's not defined right at the point, right? Okay, so here's the idea. When I write this, x arrow a means x as or x approaches a. Okay, so that means x gets closer and closer and closer and closer to a. And I mean, like approaching a means, I'm not, okay, so x is approaching a and a x is getting closer and closer, but at some point it stays away, like 2 yards away from a because a is not wanting to have x approach within 2 yards or something. It doesn't mean that. And when I say x approaches a, I mean approaches a and the distance between x and a gets closer and closer to 0. Okay, that's what I mean by approaching a. But we will not let a or x get exactly at this point a, right? Maybe I should mention that too. X approaches a means x approaches a, it gets closer and closer to a, but never actually reaching a precisely, okay? And you will hear me say this over and over, but we'll say in terms of limits, we don't care what happens when x is exactly a, but we will consider what happens as x gets closer and closer to a. So this is what that arrow means. Every time I write this arrow, that's what we mean by that in this context. All right, so let's see what happens to this. As x approaches a, okay, what happens to f1 of x? So you're thinking about x here. A good analogy to think about this is this. A is this location on the x-axis, and you are walking on the x-axis, okay? You may be over here starting to walk toward the left, toward A. You may be over here starting to walk closer and closer to A without ever touching A, all right? And so as you approach, or as you, or x, approaches A, which is the point in the x-axis, a fixed point in the x-axis, what happens to the value of the function, fx? Well, it's first like 0.7 and then 0.8, 0.9. Right? It looks like it's approaching 1, right? So as x approaches a, f1 of x seems to approach 1. And we know that f of a is precisely 1. I know we said we don't care when x is exactly a, but I am just adding for the purposes which will become clear later, I am adding this last part here. Okay. Now, as x approaches a, what happens to f2 of x? So now you're at this point, X, you're right here, you're walking, getting closer and closer to A. You're over here maybe, getting closer and closer to A. In all of these cases, it will be important for us to consider what happens as X approaches A from both directions. All right, so we'll have to consider going from the left and going from the right. As you do so, remember, we don't care what happens when X is exactly at A. You get closer and closer. At this point, your value is like 1.5. And then as you get closer and closer to A, the values, as indicated by this graph, gets from 1.5 to 1.3, 1.2. It gets closer and closer to this number 1, right? So f of 2 from both directions seems to approach 1. And what we are looking at, I hope you can see this, what we are looking at is basically these values get closer and closer to the empty hole, which is represented at the y value of 1. Right? Now, just a little note here, but in this case, f of A is actually different from 1. It looks like it's 0.5. And that's because there's a hole here, and there's a hole here, and there is a black dot where A is the x coordinate and 0.5 is the y coordinate, right? All right, what happens to F3? F3 is very different, okay? So now, as X approaches A from here, that's a little question mark, because as X approaches from the right or from the left, it differs, right? So here, let's consider this as X approaches A from the positive side. And that means you're going down this way, right? So this means from the right, this little plus sign as the superscript. This is read as X approaches A from the right, which means A is always, or X is always bigger than A. From the right, F3 of X approaches, what happens? Well, it's you're coming down here. It's like 1.5, 1.3. I'm looking at the y values as you come down this hill, and it looks like it's approaching 1, right? But as X approaches A from the negative side, from the left, it looks like f of 3 is approaching another value. Right, so now we are looking at your X, you are the X values approaching A from the left-hand side. And as you follow along this curve for these X values approaching A from the left-hand side, the value of Y, or value of F3, seems to be approaching higher and higher to 2. Okay, so now we have 2 different limiting values as you go from the right and the left. Okay, now I have 3 pictures here. And here's the important thing. For these 2, regardless of where you have a hole or not, okay, you can see that F1 and F2 are both approaching 1 from both directions, right? And in these cases, 1 is called the limit. And for this, because the left-hand limit and the right-hand limit are different, we cannot say that the limit exists for F3 at that point A. All right, let me summarize what I just said, because and I will define these things more carefully in a moment. But here's the conclusion from this first illustration. For F1 and F2, we say the limit is 1. The limit at the point A is 1. Now here's how I write this. Using green here. All right, so we say limit of F1 of X as X approaches A is 1. And this complicated notation, okay, and you have to learn this symbol very, very carefully, right? This part is not A. This is F1 of X. And this part should say X approaches A. All right, so the limit of F1 of X as X approaches A is 1. That's how you read this. Notice it's a complete sentence, okay? because you have the noun, the subject, and the verb. And the verb is equals to, right? And then we have the predicate, which is one. All right, so this is a complete sentence. Maybe I should put a period, okay? And it says, again, how do you read this? The limit of f1 of x as x approaches a is 1. That's how you read that. Also, I said the same thing about f2. The limit of f2 as x approaches a is also 1. Even though, and this is important, even though f2 of a is not equal to 1. Remember that? Because f2 had a hole right here at this point A. So f2 of A actually is 0.5, right? But, oh, so I should say this, okay? Right, all right. So the limit in both cases is equal to 1, regardless of what happens precisely when x is equal to A, as I said many times. All right, so now let's look at another illustration. So that was our first illustration, looking at these three, maybe I should say example 1. EG1 stands for example 1. Okay, EG2. I want to show you another example, which is x squared or -1 over x minus 1. So what kind of a function is this? It's a polynomial over polynomial. It's a rational function, right? A rational function could look something like this. You know, we just really, it could be something like this. You know, it's hard to generalize rational functions, but this one turns out to be a pretty easy one. Can you see why this is not so hard? Yeah, because, okay, so let's graph this. Well, the first thing you should notice is that the top can be factored. All right, so this is x plus 1, x minus 1. This is why you had to study many years of algebra before you get to calculus, you know, so you can do things like factoring. All right, so, oh, wow, this cancels, right? So you can factor this, and you can see the same factor, and you can cancel, right? Wait, can you? Well, you have to be careful here, right? Now, you probably learned you can do this. And the answer is, this is, you know, this basically reduces to x plus 1. And you're almost right, okay? But you can cancel only if what you're canceling is not 0, okay? Now, so x can't be equal to 1. Now, that's okay, because the domain of this function is all reals except when x is equal to 1, right? I mean, this is defined. So this is a rational function, and this is a polynomial. This is a polynomial. And so as a rational function, it is defined everywhere on the real line, except when the denominator is 0. And that happens only at one point, namely when x is equal to 1. So because 1 is not in a domain of f, it's okay, we can cancel this. Okay, because this is never 0. And so this turns out to be x plus 1, except at x is equal to 1. All right, so now we should be able to graph this pretty easily. Let's go ahead and use our fancy tool. And this is my fancy tool. Right. Allows me to draw these straight line segments. So nice. Okay, and now, whoops. Okay, now we draw this x plus 1. Oh yeah, that's easy to draw x plus 1. If this is 1 here, this is 0. X plus 1 is the line whose slope is 1, and the y-intercept is also 1, right? Okay, so I think I can draw mine like this. Ooh, beautiful, right? Now, why am I, oops, yeah, why am I skipping? Let's see. Yeah, the graph will look like this, basically. Now, I drew this in 2 segments because something is happening at 1, right? Okay, what happens here? Can we just put a hole here? Yeah, that's exactly right. So this function f is a straight line with a hole, with one hole where x is equal to 1, and y would be actually 2, but it's not there, right? Okay, so that's the function. Now, what happens as x approaches 1, but not at x is equal to 1. F of x approaches 2, right? From both directions. Now, you could also do things like this, you know, x and f of x. All right, so we're interested in approaching 1, so you can do 0.9, 0.99, 0.999. Notice here I'm getting really, really close to 1, right? Now, what's the value of the function? Well, the value of the function, when it's defined, i.e. when x is not equal to 1, is always just going to be 1 plus that x number. So it's 1 plus 1.9, 1.99, 1.999. Notice here, this is getting close. X is approaching 1. F of x is approaching 2, right? And you can obviously see this from the picture because this graph is just approaching the y value of 2 from the left. Now, from the right, you can also do a little XY chart. These numbers are like 1.1, 1.01, 1.001, approaching 1 from the right, right? And of course, the value of the function is still 1 plus the x value. So it's 2.1, 2.01, 2.001, closely approaching 2. You can see that from the graph as well. Okay, so this satisfies the definition, which I haven't given yet, but the sort of descriptive definition of a limit. Right? So we say the limit of f of x as x approaches 1 is 2. Again, even though f of 1 does not exist. F is not defined at 1. You see that? Does not exist. The value does not exist is the same thing as saying f is not defined at 1. All right, so f is undefined. This function is undefined at 1, but the limit does exist, okay? Because when we are finding the limits, we don't care what happens right at that point. Yeah. So say that with me for a few times. We don't care. We don't care. Okay, no, we don't care what happens when x is exactly at a, but we do care greatly what happens to f of x as x approaches a, getting closer and closer so that the distance between x and a approaches 0. Okay, infinitesimally closer to, but not precisely at a. That is what you need to remember. Okay, so hopefully you have sort of an understanding of what the limit is. So now let me define what we mean by the limit of a function. All right, throughout your study of mathematics, you will see definitions written, okay? And yeah, definitions are kind of important, right? Sure, and that's what you learned experientially in algebra and probably more in geometry, right? If you took a geometry class, or if you were fortunate enough to have taken geometry class. All right, well, let me tell you something. Definitions are like absolutely important, right? And from now on, you want to pay close attention to every definition you learn. Now, unfortunately, until chapter 2 and section 5, I am not going to introduce to you the precise definition of what a limit is, because that precise definition requires some sort of a mathematical maturity, all right? And it's kind of hard, okay? And it sounds all Greek to you in a sense, because it uses 2 Greek letters. But, all right, the intuitive definition is a good working definition for you to go by, all right? So here's the intuitive definition of what a limit is. All right, so here's a picture, okay? So this is f of x, and we say the limit of f of x as x approaches a is L. Now remember, this is a complete sentence. The limit of f of x as x approaches a, that's the subject, is equal to verb, L, the predicate or the predicate nominative. All right, so that means what? So the limit is L if and only if. Now, in most mathematical definitions, you have this word, the phrase if and only if, because what we want to do is we want to say if this part is satisfied, then the limit is L. And if the limit is L, then this is going to be satisfied. See, because we are trying to define something, it has to go both directions, right? Logically speaking. So in most mathematical definitions, you will hear or you will see me say if, or hear me say if and only if. Okay, so don't be afraid of this. This just means that, you know, this is the way to define this. And for instance, if you have to define what a dog is, which could be more difficult than this one, you can say that an animal is a dog if and only if the animal is, and it starts to describe the characteristics. Okay, and because it's a definition, it has to go both ways. Okay, so that's what we mean by if and only if. All right, so the limit of f as x approaches a is L if and only if, okay, whenever x approaches, now this is going to be really wordy because it's an intuitive definition and we are using the English language to describe what could be very concisely written in mathematics, which I will do later. All right, so the limit is L if and only if the following is true. Whenever x approaches a from both sides, I say both because there are only two directions, but not x is equal to a precisely. Okay, as x approaches a from both sides, f of x approaches L infinitesimally. That means it gets closer and closer, so that not just closer and closer, but the distance between fx and L would actually become closer and closer to zero. See, and that is the problem. When we use words like closer and closer and approaches, that is not precisely mathematically stated, right? And that's why this is an intuitive definition. But like I said, this is a good enough definition to go by right now. All right, so what does it mean? This whole thing can be summarized by saying fx approaches L whenever x approaches a from both sides. But not x is equal to a. All right, so that's the same thing. Right, and you can use this black part or the red part of as a definition, the working definition of the limit of a function. Right. Now, if there's a hole here, it doesn't matter, right? Because we don't care. We don't care? Yeah, no, we don't care when x is precisely equal to a, but we will greatly care as x approaches a. Okay, so the hole or the gap doesn't really matter. All right, so here is another example. And this time we will do something where it's really hard to find this in the in other ways or in algebraic ways. Actually, later we'll talk about this. But what is the limit of this function, sine of x over x, as x approaches 0? Okay, now notice here, f is undefined at 0, okay? Because that will give you the 0 denominator. And in fact, the top and the bottom will also be 0. Oh, by the way, because when you try to plug in 0, you get f of 0 is 0 over 0. Okay, that's not the correct answer. It's not the limit. The limit cannot be as ugly as this one. Okay, and in fact, I have told you a few times, don't ever write 0 over 0. Okay, so it's actually when you have a form of 0 over 0, it's called an undeterminate or indeterminate because we have to do something more to figure out what happens to this value. It's the 0 over 0 is not a mathematical expression that is meaningful. Right? That's why you can't say that. And in fact, you should never just use 0 as a denominator. Okay, so let me just cross this out really cross this out because I don't want anybody to see this. Okay, so now you have to figure this out. Now the graph is, okay. Yeah, I'll tell you the graph, what the graph looks like in a moment. Sometimes you have to depend on the values, all right? And so maybe what you can do is to do an XY chart and say 0.1, 0.01, and so on. And that's coming from the right, coming from the left, negative 0.1, negative 0.01, and so on. Okay, so if you plug in, and again, X is in radians, you know, as a mature adults, we use radian modes, not degrees. And so put your calculator on the radian mode and find sine of X over X, sine of 0.1 over 0.1, and you'll see 0.99833. Okay, now again, take your calculator and write or enter sine of 0.01 divided by 0.01, and you will see 0.99998. Okay, the negative, of course, this will be the same because when you put negative X in here, you have negative sine of X over negative X. So this is an even function. And so these will be the same as these values. All right. Now it's clear that this is approaching 1, right? Although you can't mathematically prove it just by these numbers. Okay. But you could safely assume, and later we will prove, that this happens to be equal to 1, even though this f is not defined at 0. Okay. So this is the correct answer. And sometimes you may have to depend on not the graph, but the XY chart. Right. Now, just so you can see the graph of this function, if you graph this on your graphing calculator, it will be something like this. See, what happens is, you know, sine of X is never bigger than 1 and never less than -1, right? And 1 over X, okay, 1 over X is this function that looks like this. Looks like this, okay. And so this is 1 over X. And so sine of X over X is not going to go above this green line. And so it hits it a little bit and hits it a little bit. And so you get smaller and smaller waves. It's like dying waves or receding waves. Okay? And on the other side is the same thing. Okay. So this is what the graph of this function looks like. And it turns out to be an important limit as we study calculus. So you may want to remember this. As I said, we will prove this before this section is over. All right, so maybe the next section, we will do that, okay? So that's how you can find the limit. All right, let's do one more before we go to the second part of this. All right, so here's a little application. We sort of referred to this in the section 1, but we can actually find the find something important. All right, so here is this problem. Let's say you have a graph of a well-known function. Let's say this is x squared. Okay, and you have this point 1, and of course this is 1, not drawn to scale. All right, let's pick another point here, which is 1 plus h. We will do this kind of thing very, very carefully later. But the difference between these 2 points is, of course, h, right? Because this point is 1, and this point is just 8 units to the right of 1. All right, and then the value of this function here is, of course, 1 plus h squared. That's the y value of this point. And of course, this point has the value of 1. Okay, so what's the slope? Of this tangent line or the secant line. You take this and what happened here? I don't want this. I think I should have taken this. Yeah, there you go. okay? That is a line connecting these 2 points of the graph, right? So that's called a secant line. The secant line between 1 and 1 plus h, the delta x, oops, the delta x is h, and the delta y is the difference between these. So the slope is going to be 1 plus h squared, that's the second y value here, minus 1. And the bottom, the difference between 1 plus h minus 1 is, of course, h, right? The top is 1 plus 2h plus h squared. Remember how you multiply things out, the square binomial. And then minus 1, and of course, these will cancel. And so this is 2h plus h squared over h. You can factor out h. 2 plus h, okay? And of course, h will cancel. Well, actually, h is not going to cancel if h is equal to 0. But again, we are thinking of this point getting closer and closer. Okay, right now, the secant, right? The slope of the secant line is precisely 2 plus h, knowing that h is not equal to 0, right? So we will do this later, more formally. But you can actually find the slope of the tangent line. Remember, the tangent line is the limit as h approaches 0, right? So as this point gets closer and closer to 1, infinitesimally closer, as h approaches 0, what's going to happen to this? Well, m, which is 2 plus h, of course, approaches 2, right? And that turns out to be the slope of the tangent line right at this point, okay? So the rate of change of this function, whose rate is constantly changing, is precisely equal to 2 when x is equal to 1. This is called the derivative of the function f at 1, right? So that's how we can use the limit to find one of those things that we were talking about earlier in section 2.1, and that is the derivative. Okay, and again, we will do many, many more examples of this. But now let's go back to studying the limit in more general ways in part 2 of this section.